record. Okay, so I believe we are recording, right? Okay, so let's get started. So before we sort of dive into the specifics of the lecture, so a couple of logistical things, right? So yeah, so this lecture is being held remotely, right? The university policy is now to resume in-person instruction, right? However, since there was some ambiguity last week, and I had sort of stated during the lecture, right, that we will be having remote instruction this week as well. That is the reason, right, why we are holding this lecture remotely. However, starting from next week, we will be resuming to in-person instruction. Okay, so please bear that in mind. So starting from next week, we will be resuming or going back to in-person instruction. So with that clarity, right? So that brings some clarity to grading as well. So the grading protocol will be very, very simple. A majority of the grading, as I had described last week, will be dedicated to your final project, right? So 85% of your class grade will be dedicated to the final project, and not just your final project deliverable, but the intermediate milestones and assignments that you all will be submitting, right, as part of that final project exercise. So you all may or may not have already seen, right, several assignments that have been released on Canvas to that effect, and I will be talking about that in just a minute. Okay, so 85% of your class grade is based on your final project. 15% of your class grade will be based on class participation, right? So what does that mean? Class participation is a loaded term. It includes, but is not limited to, your, of course, attendance, right, and engagement during the class. So I will not be taking attendance for this class, right, because I did not announce this last week, but moving forward, right? So next week onwards, we will be sort of taking a head count, right? And your physical attendance in class will contribute towards the 15%. And class participation comes in other forms as well, right? So it includes your engagement, right? Your active participation in the class, your engagement on Discord, and other aspects as well. Okay, so any questions about grading? Yeah, so the question with respect to recording, right? So will in-person classes be recorded? So I'm trying to figure that out. It gets a little bit more challenging with our speakers, right? So some of our speakers may not even be physically present, right? So they will be, right? So it gets a little bit tricky, but as long as the technology facilitates it, I think we will try our best to record all of the lectures, okay? And it's also a function of our classroom. So I believe we are in Core 101, correct? Hopefully some of you all can confirm that. So I think all of the facilities should be there in place to allow us to record our classes, but let me confirm that and get back to you guys. Okay, any questions about grading? Okay, so I see that there are no questions about grading, so let me keep going. So with that, just a few quick updates, right? So what I'll do is I'll just quickly walk over to the Discord server, and I also wanted to mention, right, that 4 assignments have been released, right? So so P0, which will be the preliminary project proposal, will be due next week. So general guidelines, so all assignments will be due at 11:59 p.m. Eastern time on a Sunday, right? So our lectures are held on Mondays, right? So the assignments will always be due on Sunday, right? Sunday, just a minute before midnight, okay? So P0, which is the preliminary proposal, will be due next week. And I believe the subsequent assignments are due the week after, right? So P1 is due 2 weeks from now, P2 is due 3 weeks from now, and P3 is due 4 weeks from now. Okay, so you all kind of have a roadmap already, right, of your expectations and your work commitments towards this class for the next month or so. Okay, so let me quickly switch over to that. Okay, so you all should now be seeing a Chrome window with Canvas, right? Can you all confirm that is the case? Okay, wonderful, right? I also just want to double check things are being recorded. Yes, I believe the recording is still active. Okay, all right. So these are the 4 assignments, right? That hopefully you all have already taken a look at. Just a quick question: do you all receive email notifications whenever an assignment is released? This is my first time using Canvas, so just double checking. Okay, so Aditi says yes. So I'll take that as confirmation that everyone receives immediate email notifications, right? Okay. All right, so let's just quickly walk through these assignments, right? So that you all know exactly what is expected of you. So P0, right? So this is, as the name indicates, is a preliminary proposal, which essentially translates into a one-page document, right? So one-pager, which has the following information: the name of the project, right? The information about the group members. So as I had mentioned last week, right? The ideal group size is 2 to 4 members. If there are any exceptions, right? Either 1 or more than 4. It must be first approved by me, right? So please reach out to me, let me know what the special circumstances are. So for example, right, you're a PhD student and you're using this class to pursue your PhD research and therefore would like to pursue it, you know, as a single, as a standalone group member, right? That would be a reasonable circumstance, right? So, okay. So as part of your submission, please provide the names and net IDs of all members, and that is important. This document will answer 3 main questions, right? So what is the problem that you are attempting to tackle? What are the main challenges towards addressing the aforementioned problem? And what is the high-level approach that you all will take, right? So what technologies, right, will you all be using? Will you all be using machine learning? If so, what specific neural network architecture, right? So some high-level guidelines, right? Sort of describing the direction that you all will be taking, okay? So this will be due the coming Sunday at 11:59 p.m. Okay, so once that has been submitted and that will go through, right, sort of a round of review by me. And once, the hope is, right, that everyone gets approved at this stage, but there may be a chance where some of you all may not, right? And that is why we will have a second round of proposal submissions, right? So due 2 weeks from now, on Feb 13th. So a day before Valentine's Day. So this will essentially be an elaborated version of the preliminary proposal. So once again, right, group members, at this point, we will, so in fact, very soon on Discord, we will start introducing you all to some of the research mentors that hopefully will play you know, an active role in this class, right? Sort of providing you all with advice on your projects, right? So if you all have interacted with a mentor, you all should state the name of that individual here. And the proposal will now sort of take a slightly more elaborated form. So you all will now be submitting a presentation, right? So not a written document, but a presentation that answers the following questions, right? So at a high level, 1 slide per question, right? Some of these may be consolidated into a single slide, but at a high level, I'm expecting 1 slide per question. Okay, so problem statement, right? What is the problem you all are trying to solve? Why is this problem of wider interest to the artificial intelligence and visual computing community? What are some of the applications, right, to the solution of this problem? What are the main challenges? How have prior researchers tried to solve this problem, right? So at this point, I expect a high-level understanding of this question, right? And in the following assignment, you all will dig into this question in much more depth, right? So how have prior researchers tried to solve this problem? Where have they succeeded? More importantly, where have they failed, right? What will be your proposed approach towards addressing these problems? At this point, I expect more details, right? A little bit more technical details on the approach y'all will take, references to any papers that y'all might be following, right? Maybe implementing, right? So that's the kind of information I expect. And yeah, contributions and evaluation plan and what will be the main deliverable. Okay, so we went over this last week. I'm just going over this again. just so that everyone knows exactly what is expected of them. Any questions so far? Okay. So Catherine Lee asks a very relevant question. Do you want every group member to submit assignments on Canvas or just one person, right? So yeah, the way I've set things up on Canvas, and again, this is my first time, it is set up as a group assignment, right? So at the time of submission, I believe Canvas will walk you all through setting up your group, right? So you all will, I guess, have to assign yourselves to a specific group, right? And the assignment will be a group submission. So my understanding is that Canvas will automatically enforce, right, only one submission per group. Okay, but yeah, so P0 will be sort of our way of testing, right, testing the system, right? So hopefully it's a smooth process, but yeah, if there are any issues, we'll hopefully have them resolved by the time P1 comes around. Okay, so yeah, so Catherine, hopefully that answers your question. One submission per group. Aditi asks, do we have to give a presentation to you or just submit the PPT? Right, so P1 will be a submission, right? But at a later date, you all will be asked to present your project, right? So that will, so essentially the P1 is a preparation for you all to start developing your slides towards a more a deeper presentation that you all will be giving at a later date, which will be announced. And that will be one of your milestones, right? So one of PN, right? Maybe P5 or P6, right? Will be a presentation. All right, okay. Any other questions about P1? Okay, no questions. So let's go back to assignments. So P2 is a literature review, right? As the name suggests, you all will compile 10 to 15 research papers and write a 1 to 2 page literature review, which surveys these papers, describes the underlying methodology, their benefits and their limitations, right? So these are the papers that you all will be reading to succeed in your respective projects, right? And again, generally encourage you all, right, to run the specific choices that you all have made by us, or in this case would be me, and potentially a mentor that you all are working with, so that we can provide you all with feedback, right, and sort of approve that these are the kinds of papers that we expect you all to be reading. In some cases, depending on the topic that you all choose, right, this count of 10 to 15 papers can also include other forms of research, right? So for example, you all could be surveying a system, right? Maybe a software tool that is especially critical towards the development of your own project, right? So we may allow that as well as part of this literature review. Okay, Karan is asking a question. So again, general note, please don't DM me. Please send the message to everyone, okay, so that everyone can see it. So Karan asks, what if we do not have a way to solve the limitations of our research problem until the deadline of the proposal? So Karan, that's welcome to research, right? So what is expected as part of your proposal preparation is for you all to do some critical thinking, right? And come up with some hypotheses, right? That, oh, these are the potential ways, right? These are the approaches which may potentially solve the limitations or the problem that you are tackling, right? There is no certainty that your approach may work, right? But you have, or your group will have put some critical thought that, oh, these are some promising directions that are worthy of exploration. And over the course of the semester, you all will explore, right? So you all will develop prototypes, you all will run experiments to develop the feasibility of your approach, and a very likely outcome may be that your approach does not work, right? And that is part of research, okay? So that's, hopefully that answers your questions. Okay, Catherine asks, one of the things that you mentioned in the first lecture is that some of the projects may be more research, others may be more development oriented. Can you explain the differences in the expectation? Yeah, Catherine, that's a great question, right? Yeah, I think, yeah, unfortunately, I don't have a specific slide for that. And maybe I should provide some more formal guidelines about that, right? But as I mentioned last week, you all have the opportunity of choosing, right, whether your project is research-centric or more development-centric, right? So on the spectrum of research and development, you can choose either one. So if it is more development-centric, then the emphasis in terms of evaluation will be more on the software development, right? The quality of the final tool or system or demonstration that you all will provide, right? As opposed to the merits, the intellectual merits, right? So there will be less emphasis on novelty, right? And research contribution and more emphasis on development. If your project is more research-centric, right? Then it will be the opposite, right? There will be more focus on the quality of technical contribution that you all are making, right? So what is the research, what is the innovation that you all are doing? There will be more emphasis on the experiments and evaluations that you all will do, and there will be less emphasis on the software, right? On the quality of your code, the quality of your software development, and the final, the polish of your finished product, right? So yeah, it's a good question. And what I'll go ahead and do is I will modify the assignments, right, to include this information, right? So at the time of P0, you all will make a selection, right, whether your project is research-centric or development-centric, right? And I'll provide some guidelines to that effect. Yeah, thank you for bringing that up. Okay. Any more questions? Okay, let's get back to it. So going back to assignments, right? So P2 will be due February the 20th. P3 is when y'all get cracking, right? So P3 will require the following sort of main steps, right? So setting up a code repository, right? Beginning your project report and sort of starting these weekly updates, right? So sort of the main deliverables for P3 are to set up a GitHub repository, right? All team members, right, must of course be members and must be active on the repo. And you all will invite me, right, as a collaborator on your repository. This is my GitHub username. If there is a mentor, then you all will be also adding the mentor to the repository, right? The second thing is what we will do is we will set up a Discord channel, right, for each group, so for each project. And you all will be using that channel to provide us with weekly updates, right? So on Monday, right? So basically every week, right? So every Sunday, you all will be expected to provide a weekly update on the channel, and I will be reviewing them at the beginning of each week. So, so for this week, right? So for P3, the channel should have the following information, right? So an updated version of the proposal, an updated version of the literature review. So essentially following up, right, from P1 and P2, and then an update of your week's progress, right? So what you all have done, any preliminary results, any experiments, right, etc. Right, and that will sort of be the protocol you all will follow in subsequent weeks. Right, so think of this as essentially sort of a log, like a blog, right, or a record of your progress over the course of this class. And in general, right, please also think of this as an opportunity for us to provide you all with real-time feedback, right? So as we sort of read these documents that you all are generating, we can sort of give you all right very clear indication about whether you all are going down the right path, or if there are any concerns we might have, we can bring them up directly on Discord. And there is a reason, right, why these channels will be accessible to everyone in the class, right? Because part of the class participation grade that I alluded to earlier, right, is an expectation that y'all sort of read and provide comments and feedback, right, on other projects as well, right? So think of this as an opportunity not only to sort of do an in-depth exploration in a project that y'all are interested in, but also be exposed to a multitude of other projects that are ongoing, right? So please think of this as an opportunity for all. Okay. So that, I believe that does it with the assignments. Any questions? Okay. So Divakar is asking, looks like P3 is not yet published. Okay, thank you, Divakar. So let me just see that right now. So if I go to, you're right, P3 is not published. There you go. Okay, so hopefully that solves that. Okay. All right, any other questions? about assignments? Okay, if there are no questions, let's move over to Discord. So, right, hopefully everyone is now on Discord. Is anybody on the Zoom call who is still not on Discord? Okay, so silence is probably a good thing. Okay, so, right, so, a general note. So please set up your Discord notifications, right, out here, right, so that you'll receive push notifications, right, on all of the announcements, etc., that are being sent. Okay, so please be sure to do that if you all haven't already done so. So yeah, we've gone through this, so I won't repeat myself. I noticed that a bunch of you all have taken the trouble to introduce yourself, so that's great. Hopefully people have already started building relations, getting to know each other. I noticed that this is still empty, but hopefully we see some activity here. We've set up a new channel, right? So the project proposals channel is a medium or a forum, right? Where, for example, if you all have a super cool project that you all would like to to describe, you all can use this, right, as the place to do so, and this will serve two purposes, right? That is the way for you all to get instant feedback from me about your project even before the assignment is due. And second, it's a good way for you all to solicit group members, right? So if you're looking for group members to join a particular project or idea, please use this channel to do so. The third use of this channel is that I will be submitting some ideas, right? So if there are some, for example, if there are projects in my group that are ongoing, I may put them here. So if that's a project that you all would like to join, you all are more than welcome to do so. Likewise, I will invite the mentors to submit projects as well, right? So if the research mentors would like to supervise a specific project or a theme, they can provide that information here, right? So you all have this opportunity not only to provide your own ideas, but also to join other ideas, right? Provided by other students as well as myself, as well as research mentors. Okay, questions? Any questions about that? Any questions about that approach? Any feedback? Okay, all right. So I see that there are no questions. Okay, let's get, so I think that does it with the administrative side of things, right? So let's go back to the slides. Okay, so hopefully y'all can now see the slides. So today, lectures, right? So in-person instructions from next week, attendance, right, will count towards class participation, right? If there is any concerns about this element, right, please let me know. Okay, so I'm gonna dive into the lecture, but if, for example, if there are any comments or questions about the attendance portion, please either put it in the chat or reach out to me later. So that brings me to the fun part of today's lecture, right? So today we will be talking about autonomous virtual humans, right? Digital humans. And hopefully that's a term or a buzzword that you all have increasingly started hearing, right? With everything that's going on in the development of the metaverse, right? So that's, digital human reconstruction has become an extremely exciting and hot topic. So hopefully I don't have to motivate this, right? But the next generation of immersive interactual virtual worlds demand functional, purposeful, heterogeneous virtual human characters, right? That are not only controlled by a user or a player, but are potentially autonomous, right? And these characters exhibit rich and believable interactions with their environments as well as other characters or players, right? And sort of with this far-reaching goal of complete immersion for an end user, right? So, and these technologies, right, have applications in a variety of areas, right? Not only gaming, right? So, ranging from urban planning, disaster and security simulations, robotic simulations, training simulations, right? So the video demonstrates a military training exercise that we conducted using a simulator that we developed, and of course, serious games. So virtual humans, right? Research addresses many different challenges, right? So it's not just a computer science or a computer graphics topic, right? It sort of looks and touches upon many facets of research, right? Touching many areas. So for example, folks that may have taken a robotics class, right? may potentially see analogies and direct correlations, right, between the ideas that are discussed in robotic motion planning, right, especially in the development of bipedal robots, right, with the kinds of research that I will talk about today in the domain of humanoid character animation, right? So there are direct analogies there. So the ideas that are used to animate virtual characters are often the same ideas that are used to control real robots, right? And there's this mutual synergy, right, between the research done in both areas. Digital humans, right, is not just concerned with the visual fidelity, right, of these virtual characters, but also how these characters express themselves, right, through natural language, right? So this requires research and advancements in natural language understanding as well as natural language generation in computer vision, right? So these virtual humans need to perceive their digital surroundings, right, in order to reason and understand about the environment, right? And of course, all of these underlying principles require advancements in machine learning, right? So a question, so as we proceed in this presentation, I encourage you all to think, right, very deeply about what does virtual humans or what does digital humans mean to you, okay? So feel free to start, feel free to post your thoughts, right, in the chat, and I'll sort of look at them periodically. So if you all had, right, your own virtual human simulator, what would you all do with that, right? What kinds of innovative applications would you all consider developing on top of such a platform? So in this talk, right, while there is certainly a large breadth of research in simulating autonomous virtual humans, right, it spans the spectrum of modeling the macroscopic phenomena of large crowds to developing monolithic agent architectures that model individual agents, right, and consider things like modeling attention in virtual agents, memory, cognition, right, inter-agent communication, right. This talk will focus on a very narrow sliver of that wide gamut of research, right. So we will focus on simulating autonomous virtual humans with real-time application, right? So the application focus here is real-time. And in particular, we will discuss key limitations in how agents are represented, right? In how these agents are controlled, right? And we will talk about things like navigation, pathfinding, simulation, how agents avoid collisions with the environments and other agents, right? How agents steer in complex situations, right? To locomotion, right? So how do we sort of take an agent controller and overlay a humanoid, right? A humanoid agent on top of that. And then we start thinking about things like animation, locomotion, right? Full body control. And finally, the ability to author these autonomous virtual humans in such a way that we aren't simply developing homogeneous simulations, right? But are developing rich, high fidelity, heterogeneous simulations of virtual humans. So let me pause for a second. Any questions or comments at this stage? I see nothing in the chat, so I'll assume there are no questions. Okay, let's keep going. So a traditional approach, right, to simulating interacting virtual humans involves many interconnected components, which sort of need to work together and sort of synergize to sort of produce this this final result. So there are many aspects, right? And let's go through them each one by one, right? So the sort of the high level layer, right, is a navigation layer, and you all must have seen topics related to this in your AI class or your robotics class, right? So navigation approaches, what they do is they pre-compute, right? They come up with some abstract representation of the environment, right? Which can be a pre-computed roadmap, or it could be a navigation mesh, right? It could be a grid, right? There are some algorithms that work on top of these pre-computed environment representations, which allow you to make efficient navigation queries, right? So the idea is that these algorithms provide the means of providing collision-free paths, right, that go from one location in the environment to another location using some optimality criteria while avoiding both static and dynamic obstacles. Okay. So there's a large body of work in this area, right, dating back to the 80s, right? So maybe, or y'all may have seen some of these ideas being discussed in the other lectures. If not, there's no problem. So potential free fields, right, are classical approach, which originated from robotics research. That essentially, right, think of the analogy here, right, that y'all want to develop a potential function that attracts agents, right, in locations which they would want to move to, while providing repulsive forces, right, in regions of the environment that they want agents to avoid, right, such as obstacles, right, or high-cost regions. And other approaches, which I won't go into details, right, include probabilistic roadmaps, again, arises out of robotics research, cell and portal graphs, of course, uniform grids, right, which are sort of the most simple discretized representation of environments. Visibility representations, which assume some kind of triangulated representation of Voronoi diagrams, for example, right? Corridor maps, road maps, and most recently, navigation meshes, right? So with anybody who has some game engine experience, right? Maybe working in platforms like Unity or Unreal, you all may have seen, right, that these are sort of the most recent discrete representations of virtual environments, right? Namely using a triangulated representation that is known as a navigation mesh that essentially triangulates the navigable surfaces, right? So all portions of the environment which can be moved upon are represented as part of this mesh, right? And on this triangulated representation, you all can do efficient algorithms that allow you to essentially generate sequences of triangles, right, that take you from one location to another. Okay. So given the ability to represent an environment and use that for pathfinding or navigation, the next problem, right, or the next thing that one must tackle is to come up with a suitable representation of the agent, right? To inject life into this environment by populating it with these agents. And one must sort of carefully consider the most compact and efficient representation of these agents, right? So we don't want to make them overtly complex, right? Because that will limit or sort of provide a computational overhead or a bottleneck, right? So for example, if one of our applications requires the simulation of hundreds and thousands of these interacting agents, right, for the purpose of modeling crowds, it is imperative for these agents to be represented in the most compact yet efficient way possible. So on this slide, right, what you all can see is an extremely compact representation of the agent, which includes its state space, so S, and its action space, A, right? So the state of an agent, right? So each the current state of an agent is denoted by the lowercase symbol S, which could potentially include simply the position, right? The position vector and the velocity vector, right? So the velocity vector sort of incorporates its direction of heading, right? As well as the speed with which it is moving, right? So this simple representation of the state space of an agent allows you to model an agent as a particle, right? That you see here, right? So the center of mass of the particle is its position, and its direction of heading and its speed of movement is indicated by the velocity vector v. So the action space then, right, is basically its acceleration, right, or the change in velocity of that particular particle, right? Executing an action, so executing an acceleration, which could be an increase in velocity or a decrease, right? Decrease in velocity or a deceleration results in a transformation of the state space, right? So hopefully you all can interpret this simple equation, right? What this is saying is that by simply producing or injecting, right, a change in velocity, right, to the current velocity of the agent, you can sort of update its next velocity, right? So the velocity at the next time step is basically v plus dv, and the change in velocity can then be used to update the position, right? So in this case, we are using the past velocity, right, to update the current state of the agent, but you could easily have used the next velocity, right? And this is an integration scheme that that many people have investigated, right? So I won't go into details for the purpose of this exercise. Okay, any questions so far? So Joe is asking, how does state space representation change when the environment is an open world? So these are very good questions, right? So this is just an example, right, of how you may model the state and action space of an agent, depending on the kind of agent you all wish to model, right? Whether it's a humanoid, a simple robotic agent, right, or whatever it is that you all might want to model, the state and action space, of course, changes drastically. And of course, as you said, it is also a function of what environment this agent resides in, right? So those are things that you all would consider as you all would develop your own agent simulations. Okay, let's keep going. So next, once agents are equipped with the ability to move, right, they need to have the ability to perceive, right? So in this simple illustration, right, we can model visual perception, right, which sort of describe the region, right? So the field of view that encompasses the different things that the agents can see, and they use that information to make their next decision, right? So in this illustration, these static obstacles and these agents which sort of fall within the field of view of an agent, right, can be used as part of the decision making of this focal agent to make its next decision, right? So you can think of this as a synthetic model of vision. So with those components, right, steering is the act of navigating an agent along the path that is produced by the navigation layer, right, while avoiding both the static aspects of the environment as well as dynamic aspects, right, like such as other agents, right? So it is during this layer where we consider other agents that might sort of potentially collide with you as the agent is moving towards its path. So again, a large body of research has been conducted in this problem of steering or simulation. At a very high level, reactive approaches, they rely on rules, heuristics, right? So you can think of them as finite state machines. So they provide these controllers which decide the next action of an agent based on its current state, right? So purely based on the current situation, I use that to make my next decision. Predictive approaches, on the other hand, take it one step further, right? Where they not only utilize the current state of an agent, but they also develop a model to anticipate or predict the future state of an agent, right? So for example, right, as this agent is moving along this path, it accounts for its future state, right, and the future state of other agents, right? So it may potentially predict, right, that there might be a collision at this future point of time, and it uses that information to make its next decision, right? So you can imagine that this is exactly how we, right, as people move about in complex situations, right? We're constantly anticipating the movements of others, right? And we use that to factor into our current decision making, right? So these are the kinds of techniques that people have been also focusing on. Data-driven approaches, right? So this sort of falls closer to the family of machine learning. So instead of handcrafting rules or handcrafting algorithms, they rely on learning these policies directly from observations, right? So if we have data obtained from the real world of how people move and navigate, we can use that data to automatically learn and infer policies, right? And at the other end of the spectrum, right, we have planning-based approaches, right? And again, these are ideas that originate from robotics, which plan not only in space but also in time, right, to come up with space-time collision-free paths. Okay, questions so far? Okay, I see no questions, so I'll keep going. So once we have a planning and steering layer, right, the next step is then to overlay a locomotion model, right? Oh, there's nothing. Okay, so there was a video there. But yeah, so to overlay a humanoid locomotion model, right, which tries to follow the path that is generated by steering as closely as possible, right? And hopefully y'all can see that, or y'all can appreciate that there is a disconnect, right, between how the steering layer works, right, which probably assumes some simplified particle-based representation of an agent, and how we as people move, right? So if you visualize the trajectory of the center of mass of a biped, it is fundamentally oscillatory in nature, right? So it sort of oscillates, right? whereas the trajectory that would be generated by a particle simulator would usually be a reasonably smooth curve, right? So this disconnect is something that one must carefully consider, right, when modeling locomotion in humanoid virtual agents. And finally, right, we sort of have a behavior authoring framework that sort of sits on top, which provides tools to end users, right, to be able to specify and automatically generate complicated interactions between multiple agents in dynamic environments, right? So these behavior authoring is usually in the form of scripts, right? So usually as programming scripts or maybe some other form of script specification, which is usually the task of a specialist, right? And end users are usually provided with some parameters which they can tweak, but they're not often able to sort of fundamentally author or alter the underlying simulation. So I see that there's a comment. Aditi is asking, sometimes a collision is practical. Example, two cars sometimes do collide and accidents happen. So avoiding collision every time is not 100% realistic, right? So does the system let the particles collide sometimes? So Aditi, that's a very interesting question. So it's a function of what it is you're trying to simulate, right? So if I'm trying to simulate collision-free phenomena, right, then that would be what you all would encode in your system. But if, as you said, collisions are part of the required phenomena that you wish to simulate, right, in the example that you described, and you can of course think of many examples, right? So if you're modeling inanimate physical entities, right, like like fluids or smoke or cloth, right? So they don't have their own active controller, right? They simply respond to the laws of physics, right? So those objects will fundamentally collide, right? And modeling collisions and resolving collisions, right? So how do these physical objects, right, deform and manipulate in the presence of collisions? So that is something that is a part of the physical simulation in that case. For the purpose of this discussion, we're talking about autonomous beings, right, who are trying to avoid collisions as best as they can in this particular simulator. Okay, but that's a good question. Okay, let's keep going. So a lot of work again in behavior authoring. I won't go into too many details, right? So they range from using scripts to rule-based ideas to more deeper cognitively based approaches, right? Where agents are literally modeled from the cognitive layer, right? And authoring entails specifying properties pertaining to cognition, right? So these are the kinds of different ideas that have been explored in this domain. So all of these systems, right, sort of come together. So the pathfinding, steering, and locomotion layers come together to sort of produce these homogeneous simulations, right? So where these humanoid characters are sort of moving about in seemingly similar fashion. However, heterogeneity, right, is something, and there should have been a video playing, but so heterogeneity amongst virtual agents is usually injected at the authoring and visualization layer, right? So in the visual appearance of these humanoid agents. So before I sort of dive into the ideas that we have been looking at, right, I just want to sort of present sort of some of the open source solutions. And these are a little bit outdated, but certainly worthwhile exploring for folks who are doing research in this area, right? So I won't go into too many details, but a lot of these technologies, right, make many of these solutions extremely available and accessible to you. And in recent iterations of these game engines, these solutions are often actually part of these game engines, right? So Unity, for example, has many of these technologies that are part of it, which you all can just use out of the box. So as I was mentioning, right, that there are certain key limitations in how we traditionally simulate autonomous virtual humans, right? And this is something that we will talk about over the course of this lecture, right? So it requires sort of careful consideration of each of these elements which need to be addressed in order to derive a proposed model. So in the rest of this lecture, right, what we will do is we will identify only a handful of these limitations. and come up with proposals, right, of how we might address these limitations, right? And the idea here is for you all to already begin thinking in a similar fashion as you all develop your own project proposals. So the first thing we will talk about, right, is a limitation in these simplified agent representations and these reactive control policies. And the approach that we will take is a footstep-based representation of humanoid agents, right? And a planning-based control framework where these agents are able to sort of extrapolate the future state of other agents while making their own navigation decision. The next thing we will talk about briefly is the lack of coupling between steering and navigation, right? So the pathfinding layer and the sort of the low-level control or steering layer. And we will talk very briefly about the potential use of multiple problem domains of representation and an integrated planning solution that can work across multiple domains of control. And finally, we will talk about how these agents traditionally only have visual perception and they lack multimodal perception. So we present this framework which sort of accounts for how virtual agents can actually hear sounds in the environment. And finally, I don't know if we'll get to all of this, right? But to address the lack of an appropriate interface for authoring multi-actor simulations, we will talk about an event-centric authoring framework, which uses what we refer to as parameterized behavior trees. And finally, we'll sort of bring all of these solutions together, right, in sort of this one single framework that we've provided as an open source solution. And this is actually a framework that students use in the computer graphics class that we teach. Okay, so any questions before I dive into it? Okay, I see no questions. So the first limitation, right, is essentially a simple particle representation and a vector control representation of how agents move cannot capture the capabilities and constraints of human locomotion, right? So hopefully this is a fairly obvious statement to you, right? That we as humans, right, rely on the complexities of our morphology, and that cannot really be represented in a simplified particle-based approach. So furthermore, the current state of the art in these control policies, they can only handle a fraction of the scenarios that agents would typically encounter in dynamic virtual environments, right? So this analysis that you see on the slide, it sort of plots the coverage, right, of different simulation techniques, right? So each of these curves is a different control framework. And what coverage essentially measures is the ratio of the number of situations that each of these policies was able to successfully handle, okay? So I won't go into too many details, but at a high level, what you all can see is that each of these policies is able to sort of at a maximum, right, solve roughly 60% of the scenarios that agents typically encounter, right? So this coverage is pretty low. So we need to be able to do better than this. And you can sort of visually see this as well, right? So this simplified agent representation and these reactive policies produces many visual artifacts, right? Such as sliding in these crowded situations, live blocks, right, in narrow passageways, right, where these two agents are trying to sort of squeeze to go through a doorway. And even violation of simple orientation constraints, right? So this is not how we as people move. However, this is something that arises as a result of this simple representation. So a particle, right, does not conform to the constraints and capabilities of bipedal human-like movement, right? A vector-based interface does not have enough information to indicate certain maneuvers, such as sidestepping, reorienting your torso, stepping backwards versus turning around, right? So, so when you sort of overlay how a biped, right, is trying to walk, right, you can see that it creates this discontinuity and this disconnect between the low-level steering level. So to offset these limitations, right, we fundamentally ask, why not represent the footsteps that humanoid agents take at the control layer, right? And that's essentially the proposal that we wish to take. And to provide this richer space, both state and action space, for goal-directed collision avoidance, where the controller is essentially synthesizing a sequence of footsteps that the agent will take to move in a virtual world. And this footstep-based interface naturally provides a much tighter coupling with the locomotion layer, right? Where it is much more intuitive to overlay a humanoid to follow a sequence of footsteps as opposed to following a center of mass trajectory. And this is essentially what our work does, right? So our work is generating biomechanically plausible footsteps for an agent to navigate in complex dynamic environments, and it provides this tighter coupling with animation to produce more natural, human-like collision avoidance, right? And this is what you see in the video. So how does this all work? So the state and action space that we saw previously, right, which was a particle-based representation, we extended. So we extended to include the position and orientation of the support foot, right? So the X here is the position of the support foot, and theta, right, is the orientation of the support foot. And an indicator function, which indicates whether the support foot is the left foot or the right foot, right? So as y'all are looking at this, maybe y'all are wondering, how does the state space represent both feet, right? Because I'm only representing one foot. So do you all have an answer to this question? Anybody? Do you believe that this state representation, which considers or which models only a single foot, how is this able to sufficiently represent bipeds, which have 2 feet? Any thoughts? Center of mass. So Aditi says center of mass. So maybe you're implying that given the center of mass and given the position of one foot, I can extrapolate the position of the other foot. So it's an interesting idea, not quite the right answer. Anybody else? So Divakar is saying by alternating left and right. So I think Divakar is perhaps onto the right thing. So some interesting ideas here, right? Okay, so let me give you the simple answer. So it's actually very simple. We only consider modeling a dynamic humanoid agent. What does that mean? A dynamically stable humanoid agent is an agent which is in a state of movement, right? So it's walking or potentially running, right? So if you'll think about that very carefully, so when you all are walking, right, at any given point of time, at most one of your feet is making contact with the ground plane, while the other foot is in the air, right? So it's swinging, right? Therefore, when thinking of this as a control problem, it is sufficient to only explicitly model the foot that is in contact with the ground plane, right? And there is no real need to model the swing foot, right? The foot that is is currently in the air, right? And as Divakar said, as you're walking, you're alternating between the support foot, right? So your left foot is making contact with the ground plane, followed by the right foot, followed by the left foot, right? So that's essentially the idea. Naturally, if the humanoid agent is at rest, right? So if it's in a statically stable state, that means that both feet must be planted, right? In that case, we would need a separate representation. Yeah, so Divakar, yeah, I just answered that question, right? So if we were not just walking, if we were standing, then this model would not be sufficient, right? So this controller is only working for agents that are in a dynamically stable state, right? And the word dynamic, or the term dynamically stable, is actually a very loaded term, right? So I sort of briefly touched upon, agents may be running, agents may be jumping. So I would leave it as an exercise for you all to think about what happens when in these other forms of movement, right? When you are running, is one foot always in contact with the ground plane or not? Okay, so you all may want to think about that. Anyway, Karan is asking a question, but the orientation of the foot in the air determines whether we are taking a large step or a small step. can we model that using this representation? Karan, that is a wonderful question, right? And as I describe the control strategy, hopefully I will answer that question. Okay, let's keep going. So that's the state space, right? The action space is actually a three tuple, right? So it's no longer just a single change in velocity, but it has three elements. And Karan, I think this will answer your question. So the action space involves the selection of three parameters: the time period of the flight phase, right? So that's the amount of time that the alternating foot is in flight. The desired speed of the center of mass at the end of the flight phase, and the orientation of the center of mass trajectory during the flight phase, right? So this is essentially, Karan, what you were describing, right? So this will encode the orientation of the trajectory that the center of mass of the biped takes over the course of this single footstep. And I'll visualize this in just a second. Okay, so this is essentially what it looks like, right? So the movement of the character over the duration of a single step is defined as a 2D analytical approximation of the dynamics of an inverted spherical pendulum model. Okay, so that's a mouthful. So for those of y'all who have taken a robotics class, or maybe even watched a YouTube video about how humanoid robots are controlled, so the key insight that roboticists have made over a very long period of time is that if you look at the motion of an inverted pendulum, right? So if you look at how the ball of a pendulum moves, right? If it is inverted, right, it follows a hyperbolic trajectory. And researchers have found that that movement very closely resembles the movement of the center of mass of a humanoid as it transitions from one support foot to another support foot, right? So that kind of movement, right, is very similar. And researchers have deeply studied the spherical inverted pendulum model, and they have these physical equations of motion that govern how that model moves, right? So we can use those physical equations and apply them in this context, okay? And that's essentially what we're doing. And we're taking it one step further. So we're taking that hyperbolic equation and we're reducing it, right? So we're coming up with an analytical approximation of that. So we're reducing the third order term of a hyperbola and simply looking at it as a parabolic equation, okay? So I won't go into too many details here. But essentially, we can use this parabola, which is defined using this equation right here, right? So where you see the x term and the y term separately. And we can use this to estimate the movement of the center of mass of a biped over the course of a single footstep, okay? And then these terms, right? So these are varying curvature, the speed of movement, and the step size, right? So by adjusting these terms, we can essentially adjust, right, the anticipated movement of the center of mass, right? So hopefully this visualization communicates that by sampling through the action space, right, of possible parameters of movement, we can see how the center of mass would move depending on where I would plant my foot next, okay? And this is just another illustration, right, where we can also sample not only the curvature and acceleration of the center of mass, but we can also sample the orientation of the foot. And this will also have an impact on how that parabola changes. So I won't go into sort of the innards of the math here, right? But I'm just trying to give you all a high level understanding of how you all can set up a control problem, right? And proceed to solve it. So, so Divakar is asking, why do we have T in the action space? Isn't time period global? Why is it specific at each action? So that's a great question, Divakar, right? So T, or the time period here, is the time period of the flight phase, right? What does that mean? It means that it is the amount of time that my foot is swinging in the air, right, while the support foot is making contact with the ground plane. So it's not a global property, it's a local property that is specific to the time period or the duration of this single footstep. Okay, so hopefully that answers your question. Okay, let's keep going. So now that we've developed or defined the state and action space, the next question is to define the cost of taking an action, right? So before we can devise an algorithm that decides which footstep to take, we first need to objectively measure the cost of taking an action, right? So, so in order to define this criteria, we define these three cost terms, right? And this is essentially an energy formulation that hopefully you all can start taking, start looking at. So the first term, right, is essentially a fixed rate of energy which the character expends per unit time. So T here, right, is the time duration of the footstep, and R is a constant term. So this is essentially a fixed penalty term that penalizes the longer the footstep is. The second term, and hopefully this equation looks a little bit familiar to you all, right, is essentially the amount of energy required to maintain a desired speed, right? So if you all just look at this portion of the equation, can someone tell me what this term is? m/2 v squared, anybody? Anybody know what this, the left-hand side term of this equation is? Very good. So current kinetic energy, right? So half mv squared is kinetic energy, right? So, so what this equation is trying to do is it's trying to define the amount of energy it takes to maintain a desired speed, right? So which is essentially the kinetic energy in the system. So if you just look at the left-hand side of the term, right, that's your is half mv squared. So then anybody knows what the right-hand side is and why do we subtract it from the kinetic energy? Anybody? So in a pure system, right, where there is no energy lost, all you need is to inject the kinetic energy into the system, right, for the system to move with a desired speed. But this is not a perfect energy-free system, right? Some amount of energy is constantly being lost due to something, right? So can somebody tell me what that energy loss is? Okay, so Behzad is making a good comment, a gravity-based energy loss, right? So you're on the right track, Behzad, but not quite. Anirudh says conservation. Okay, Divakar says friction, very good. So whenever, right, a humanoid plants his or her foot, right, on the ground plane, a certain amount of energy is automatically dissipated, right? And that is denoted by, V sub 0 cos 2 theta. Okay, so I won't go into the geometry of this right now, but this much energy, right? So half m and this velocity term is automatically dissipated into the ground plane. And therefore, a character needs to constantly keep introducing and reintroducing, right, new kinetic energy into the system in order to maintain the desired speed, right? So that is the energy loss, which we are trying to model here. And again, we're doing this at a very simple level, right? But hopefully y'all can appreciate what we are trying to model here. Okay, so E2, right, it captures only the cost of changing a character's momentum at the beginning of the footstep. The character's momentum may also change over the course, right, or during the trajectory, right, during the center of mass trajectory. So for relatively straight trajectories, this change in momentum is mostly due to the passive inverted pendulum dynamics, and that requires no active work. However, for trajectories which have curvature, which is often the case, right, with a biped, you need to inject additional energy into the system, right, which is essentially the change in momentum of that system, right? And this is essentially what we're trying to model here, right? So it's basically the momentum as a function of the length, right, of movement of that center of mass, which is modeled in E3. Okay, and finally, right, we come up with a heuristic function. So again, for folks who have taken an AI class and who have perhaps been introduced to planners like A star, so this cost function, right, gives you the cost estimate of taking a specific footstep. We further want to anticipate, right, the total predicted cost of reaching a particular destination, right? So for example, of taking n footsteps. So we therefore have sort of an admissible understanding of the heuristic of taking n steps into the future, right? And this is not an accurate estimate, right? It's very much an approximation. So once we have all of these systems, right, once we've modeled the state space, action space, and these cost functions, we can now rely on a planning-based approach to start generating a sequence of footsteps, which takes the agent towards a desired goal while minimizing the total cost of the system, right? So that it's essentially a cost minimization problem that we are trying to do. So you can use either a planner, you can use some kind of a numerical solver, right, to solve this problem. So I won't go into the details of that, but at a high level, this is how we set up this control problem. So now let's start looking at some examples, right? So we started this whole discussion by saying that particles are insufficient, right? And therefore we add complexity into the system. So a U-turn is a wonderful example of how we move, but something that a particle fundamentally cannot model, right? So you can see that the first step that we take sort of changes momentum towards the desired direction, right? However, because of orientation constraints, the second step cannot be immediately oriented towards the target, right? And you need to take a third step in order to complete this, 180-degree turn, right? So something as simple as taking a U-turn sort of naturally arises from this control problem. So just another illustration, right? With such a setup, we can now, alter the parameters of movement, and we can start, creating different gait morphologies, right? And so, right, for example, we can start, modeling humanoids which are tall, wide, narrow, short. And I think in this illustration, we were even trying to model a humanoid agent which had a limp, right? And this is by asymmetrically modeling the left foot and the right foot, right? So these are the kinds of things we can start doing by introducing more depth into the controlled representation. Okay, let's now talk about collisions, right? So instead of having a single particle representation, this video kind of sped up, right? But we sort of have a more complex representation of the collision representation of a humanoid agent, right? So what you're seeing in this simulation is where a simple particle representation would actually produce collisions, right? And those would be false positives. However, using this more sophisticated representation of collision representation as well as control, we can see that these humanoid agents are able to sort of get significantly closer together, right, in this egress or evacuation simulation as compared to what traditional particles would have done. So in this demo, right, we can sort of see that these autonomous characters are sort of walking through these narrow passageways. So the next doorway is so narrow that only one single character can squeeze through, right? So previous methods would have sort of produced a live lock where these agents would have collided. But in this planning-based approach, we can see that the agent in orange, right, sort of takes this subtle sidestep towards the side, allowing the other agent to pass through before it proceeds to make its own way through the passageway, right? So these kinds of sort of controlled policies naturally arise by having a more sophisticated planning-based controller. And finally, right, by taking some efficiency considerations, we can use these control frameworks not only to simulate a single agent, but to simulate hundreds of agents, right? So you can simulate thousands of agents at real time using such an approach. Okay, so let me, hopefully this video works. Okay. Right, so this is now just sort of another body of work which shows, so in the previous method, I simply talked about how we can synthesize trajectories of footsteps, right? I didn't actually talk about how we can animate humans. So in this video, I'm simply showing, right, a data-driven approach of how we can create an animation controller that is able to very accurately follow the footsteps that are provided as the next movement decision, right? So I won't go into any details here, but at a very high level, what we're trying to do is we're taking a collection of motion capture data, right, that sort of corresponds to different footstep decisions, and we're generating a blended motion representation where what you're seeing, right, this triangulated representation that you're seeing on the ground plane, each point in this triangulation represents a specific motion capture, right? And it corresponds to a specific location where you can plant your foot. So what we can do is we can sort of do a blend, right, of discrete motion clips that correspond to specific footsteps, right, to produce a continuous representation where the agent can plant its foot at any location, right? And we can blend between those motion clips to synthesize a new motion that allows us to animate the character with that specific footstep motion constraint. Okay, so at a high level, that is what this approach is trying to do. Okay, so I see no questions. So if we go back to our original coverage analysis, right, we can see that this new approach that we have developed is able to produce significantly better coverage, right? So we can now solve approximately 80% of the scenarios that these agents typically encounter. However, right, 80% is arguably still not sufficient, right? So there is a lot of work that still needs to be done in order to develop an efficient approach that can produce perfect coverage. So what this curve is showing, right, is essentially an offline oracle, right? So it's a space-time planner that has an infinite time budget, so it works offline. And what we are proving here is that as long as a controller has enough time, right, enough processing time, it can generate a globally optimal solution, right? So it can produce perfect coverage. However, the challenge is, right, that we want such coverage in a real-time system. Okay. All right. Catherine's asking, how are the possible scenarios determined, especially since it was mentioned earlier that it is not possible to cover all scenarios? Catherine, that is a wonderful question. So I encourage you to take a look at this paper, right? Scenario space, which characterizing coverage, quality, and failure of steering algorithms, right? So this comes up with a way of representing and sampling the scenario space of agents and crowds. Okay, so you're absolutely right. There's no theoretical or grounded way of quantifying all possible scenarios, right? So what we come up with is an approximate discrete representation of this space, and we come up with strategies to sample the space. Okay, so please take a look at this paper. Okay, so why don't I pause for a minute, take a sip of water. If there are any questions, please let me know. Okay, so I see no questions, so let's keep going. So moving along, so current approaches, right, they essentially pre-compute roadmaps or navigation meshes, right, to efficiently query paths for static environments. And steering is responsible for factoring in dynamic things like other moving agents or moving obstacles. So the next generation of applications would require high fidelity navigation in extremely non-deterministic and dynamic worlds, right? So we even want navigation to factor in dynamic aspects. So this problem, right, the problem domain of interacting autonomous agents in dynamic environments is extremely high dimensional, and it is continuous. And there are infinite ways to interact with objects and other agents, right? So what Catherine was alluding to, right? This scenario space is extremely high dimensional and continuous space. So a rich action set with intelligent decision-making facilitates robust virtual characters, but at the expense of scalability, right? And if you simplify the problem, right, so you can have efficient simulations, but with extremely simple behavior. So one possible idea is, instead of a single domain of representation, we can have multiple domains of representation, right? So we can have a particle-based representation, we can have a footstep representation, we could have a fully articulated humanoid, right? And the control problem then is to decide which representation to use when. Okay, so that's kind of how we can sort of think of this problem in a slightly different way, right? So what this would need is a planning-based control framework that is able to efficiently work in multiple problem domains at the same time. Okay, so this is sort of an illustration, right, where we have sort of a fully humanoid control framework that is able, I mean, the problem may seem trivial, but this is an extremely complex space-time problem to solve, right? And what these notoriously challenging deadlock scenarios are something that we can solve using this multi-domain representation, right? Where these controllers are able to produce collision-free trajectories, not only in space, but also in time. Okay, so I won't go into detail here, but at a very high level, the intuition here is that instead of relying on a single problem representation, we can rely on multiple domains of representation. And we can think of a planner, right, that is able to efficiently operate in different domains of control depending on the complexity of the scenario. Okay, so if anybody wishes to dive into this in more details, I can link the paper, and it's, yeah, I'm sure y'all can find it online as well. Okay, so let's now switch gears. There was a quick question, so so Aditya asks, how are these models implemented programmatically? Is there any repository which we could download and check in our local system? So it's a good question, right? A lot of these solutions are available open source, right? And I will leave it as an exercise for you all to find these frameworks. As I also mentioned, depending on what environment you all use, right? Depending on what platform you all use, some of these solutions may even be available out of the box, right? Some of the more sort of cutting edge work may not be available, right? But y'all can more generally get a lot of these algorithms and methodologies available to you, right? And I can certainly help. So if y'all are, for example, thinking of a research project in this area, please reach out to me and I can point you all in the right direction. Okay, let's keep going. So this video, right? So now we're sort of zooming out. So we're now dealing with these large crowd simulations, right? And we are asking our questions that how can we optimize the behavior of these large systems, these large dynamical systems, to produce a specified criteria, right? So again, I won't go into details. I'm simply exposing you all to these ideas. So we can think of a crowd simulation as a very complex physical system, right? Where each agent has particles that govern how it moves, right? So if we expose all of those parameters to a global solver, to a global optimization layer, and the task of that solver is to select the parameters of movement of each individual agent in order to produce or optimize a global objective, right? We can actually solve for that, right? So for example, at a very high level, if we wanted to produce a movement of crowds that minimize the amount of time that it would take to evacuate a building, right? We can actually search through the space of crowd movement parameters and derive a movement strategy that achieves that complex dynamic, okay? So these are the kinds of questions that we can ask with these kinds of solutions. So the challenge is that how can we efficiently search, right, through the space of these parameters? So if you think of crowds of thousands of agents, that's an extremely high dimensional system. So the algorithmic challenge is that how can we come up with an optimization strategy that can efficiently work, right? And the solution that we take in this approach is essentially to use evolutionary optimization algorithms, right? And the specific approach that we use is known as CMA, which stands for Covariance Matrix Adaptation, right? So at a very high level, you can think of that as an evolutionary approach to solving this optimization problem. Okay. The dual of that problem is, instead of searching through the space of crowd movement, we can search through the space of environment configuration, okay? And I'll just tease this today, and I'll talk about this in much more depth in a later presentation. So the idea here is, again, very simple. Can we automatically reconfigure the configuration of an environment to optimize certain criteria that we can extract from a crowd movement, okay? So can we automatically adjust the pillars in a hallway, right? Can we automatically slide and move the walls in order to produce certain criteria, desired characteristics of crowd movement, right? So these are the kinds of questions that we can ask. And once again, you can think of this as an optimization problem that we can solve for. Okay, let's keep going. Let's do a quick time check. Okay. Any questions so far? Okay. So moving on to perception. So as I mentioned, current approaches only model visual perception, right? So they model synthetic visual perception models of how agents can see in their immediate surroundings. So auditory perception is something that is sorely missing. So in these current simulations, you can start sort of producing these agent models which can sort of move about in these complex environments based on what they see, right? But to offset this limitation, we have now developed frameworks of propagating sounds in these environments, right? And actually have agents which can perceive what they think they heard, right? So I don't know if you all can actually hear the sound, but it doesn't matter so much. So what's important for you all to see, right, is that these labels that you'll see on the top of every agent, let me actually turn off the audio. Right? So the labels that you'll see on top of these agents is essentially a perception of what they believe they heard. This green arrow, right, is a sound trigger that is happening in this virtual world. What y'all, I'll wait for the next sound to be triggered, right? Yeah, there you go. Right? So y'all would have seen, right, that these waves of, right, these sound waves that are disseminating. So that's essentially the sound being propagated into this environment. And as y'all can imagine, as the distance from that sound source increases, right, the sound degrades. So agents that are directly in front of the sound source are able to accurately perceive what they heard, right? So that's the label in green. And depending on how far away they are or whether they might be occluded, right, by the presence of other agents or obstacles, their sound perception accuracy may degrade, right? Where they may only have heard something, but they can't automatically distinguish what they heard, right? And in some cases, they may even incorrectly perceive what they heard. So how does all of this work, right? So there are sort of three main stages to this framework. So during an offline process, right, we take a continuous sound signal and we sort of adaptively discretize it in the time and frequency domain, right? So this illustration on the left-hand side is essentially the short-term Fourier transform of a sound signal. So what we've done is we've come up with a more compact representation of that sound source, right? So and we call this the sound packet representation. We're essentially consolidating, right, all of the sparse information in the Fourier representation to come up with a more compact representation of sound. These sounds, right, in a database of sounds are then hierarchically clustered and categorized based on a human perceived similarity measure, right? So we essentially conducted a user study where we sort of categorize the similarity between these different impulsive sounds, okay? So this tree that you see is essentially a hierarchical categorization of these different sound sources, right? So these sounds, right, so we've come up with these pre-computed packet representations of these sounds. So these sounds are then propagated in these dynamic virtual environments, right? So what you're sort of visually seeing, right? So we've come up with this discrete representation of the environment. So we can sort of look at both a uniform representation as well as an adaptive quad-based representation. And we can essentially propagate sound, right, through these virtual environments, right? So as you all can see, that as these sounds collide of obstacles, right, and other aspects of the environment, right, they reflect, they refract, they even sort of undergo dissipation, right? So as the sound travels further, it eventually attenuates and dies out, right? So these are the kinds of properties of acoustic simulation that we can model using this approach. So for those of you all who are wondering, right, what is the actual approach? The idea here is very simple. So the algorithm we use is essentially a wavefront propagation algorithm, right? So the specific algorithm is known as the transmission line matrix method. So y'all can Google it and Google acoustic simulation, and that's probably the first algorithm that y'all will see. So, so as I mentioned, right, our framework is able to use the sound propagation model to capture these different acoustic properties, right, including absorption, diffraction, reflection, right, and so on and so forth. And it can also sort of work for dynamic virtual environments, right, where there might be multiple signals, right, that might sort of convolve, right, and confuse one another. So the sound signal, as it attenuates due to propagation, it results in a decrease in the amplitude and an increase in the frequency interval of each sound packet, right? So that sound packet representation that I described earlier, as the sound travels further and further, its amplitude decreases and its frequency intervals increase, right? So it results in a degradation in the frequency layer. So this distorted sound signal is then perceived at a receiver, right? So at the location of an agent, right? We essentially have a sound perception model which tries to understand what it thinks it heard, right? And it compares it to sounds in the database to find an accurate or an approximate match. And there are two steps to this process, right? So the first step, what we are doing is we are selecting a set of sound candidates from this database, right, which are approximately close to the sound that was received. And the high-level idea is that we're essentially comparing the frequency interval of each packet in the sound sequence as it corresponds to the sound signals in the database. And the second step, right, is essentially to use what is known as dynamic timed warping. This is an algorithm which is used for sequence matching, right? I'm sure you may have seen this in an algorithms course. So we're essentially matching the sequence of sound packets that is received at the receiver, right, with the original unattenuated sound sequence packets that are present in the database. And we find the closest sequence match. So if there is a high similarity measure, right, it results in an accurate perception. And if there are multiple sources that sort of approximately match with the attenuated signal, right, that instead of choosing the leaf node, we essentially choose the lowest common ancestor, right? So this produces an approximate perception, right? And this sort of approximation increases, right, or gets coarser and coarser depending on the sound degradation. Right? And in some cases, it may even produce an incorrect perception, right? So if the sound signal has degraded significantly, it may actually result in an incorrectly perceived sound. Okay, so I'll skip through some of these results, right? But you can sort of take this framework and we can start modeling virtual agents that essentially not only see, but they also hear sounds in the environment, right? And you can sort of use that as part of their behavior framework, right? So they can consider what they heard and sort of account for that in their decision making. Okay, so let me skip through some of this in the interest of time. So I've just a demonstration of how you can sort of account for sound as part of an attention framework. Okay, I'm skipping this. Let's get to an interesting demo. Okay, so this is a game prototype that we developed. Can you all hear the sound in the presentation? Probably not, right? No, okay, no problem. That's fine. So let me describe what is going on, right? So in this video, yeah, so this is sort of a base game, right? Where these NPCs, these robots, they can only see, right? But they cannot hear sounds in the environment, right? So as you can see in that demo, that robot, right, was essentially dormant until the player sort of entered its field of view, right? So it sort of produces this unnatural behavior, right? This robot does not react unless it actually sort of sees the agent. So what we did is we created a version of the system where these agents, these robots were now blind, right? They're blind, but they can actually respond to auditory signals, right? So this robot, right, as you can see in its decision system, right, it can hear the shooting sound, right? And it can even call out for help, and other robots can respond based on what they heard, right? So we're simply demonstrating the potential of how we can have a sound propagation system and how that can be used to enhance non-player characters. Okay. Let's see some comments. Oh, yeah, sorry, yeah. It wasn't critical, so I didn't do audio share, but I'll try to do that next time. Thank you. Any questions about the technical aspects or about the project in general? Okay, so I think, yeah, I don't see any other questions. Let's keep going. Okay, so the next thing I'll talk about, right? So I mentioned that it is extremely challenging to come up with behavior systems that author multi-actor interactions, right? And the complexity of authoring characters and interaction between characters exponentially grows as we diversify the possible actions that each virtual character has, as well as increase the number of characters that interact. So in order to make this problem tractable, right, we've developed what is known as an event-centric approach, where actors are participating in events, right? So where actors who participate in events, they temporarily suspend their autonomy and are exclusively controlled by the event to ensure coordination between actors, right? So at a high level, you can think of this as a hybrid approach where we're combining decentralization and centralization, right, to achieve complex multi-actor behaviors. So this is essentially the graphical formalism, right? So these are behavior trees, which some of you all may or may not have seen. And we sort of modified these behavior formalisms that were invented in, from operations research and used it for authoring multi-agent behaviors in computer animation. So I'll simply show you all how these behavior trees work, right? So this is essentially an illustration of how these behavior trees are being used to essentially author a simple conversation between these two characters, right? So as you can see that, these characters are sort of instructed to arrive at a common meeting place. They look at each other and they sort of perform these gestures to sort of encode a conversation. And the main advantages of the system is that the authoring complexity of these behavior structures, right, scales linearly in the complexity of each individual agent as well as the number of participating agents, right? And this is due to the modular and hierarchical nature of these formalisms. Okay, and finally, right, in an effort to bring all of these solutions together, we've sort of developed this framework which we refer to as ADAPT, right? So ADAPT essentially combines these navigation and steering systems, these animation systems, as well as these behavior authoring systems, right, into one single framework which you can use for multi-character control. So I didn't talk too much about the animation system, right? But what we can do is using a data-driven animation framework, not only can we play a single animation clip that controls the entire body of a character, but we can overlay different animation clips that are being used to control different parts of the body, right? And by blending them together, you can essentially sort of produce a complex animated system, right? Where we may potentially have gaze tracking controlling the upper body, reaching controlling the right arm, right? Physics controlling a part of the body which responds to physical forces, right? Sitting, locomotion, different gestures, right? And all of these systems get blended together to produce the final pose, right? So it's essentially a complex blending system that can be used to control an animated virtual human. So yeah, in this demo, this is essentially a demo, right, where we can sort of have a walking controller along with a gesture controller, along with a gaze controller, right, all working in tandem to control a single avatar. Just a demonstration, right, of how you can sort of combine a kinematic system with a physical system, right? So this is a system that is being controlled using motion capture data, but it can also respond to physical forces. And finally, right, this is just another illustration where you can even have other forms of control, right? So we essentially have a Kinect-based control, right? Where this character is essentially following the movement and gestures, right, of these two people. One of them is me. So then we can essentially start creating these simple game experiences. Okay. So I'll walk through all of this. So all of this now comes together, right? And then this is just a simple demonstration of a reasonably complex story, right? That we can now begin to author using all of these different interconnected components, right? And we can use this library of reusable behaviors, which can then be instantiated between, based on different events that happen in a scene, right? So events, once active, can be successfully executed or potentially even interrupted, right, based on triggers or other dynamic events. So this sort of creates, this rich heterogeneous simulation of multi-active behaviors that begin to start acting out complex stories, right? And I'll stop this here, right? But I'm sort of alluding, right, to what's next, right? What's potentially next is that how can we use these autonomous virtual human control frameworks to be able to create interactive digital stories, right? How can we sort of co-opt and control these characters to tell meaningful narratives, right? And this is something that we'll talk about in a later lecture. So I'm going to end the lecture here. Let's have some time for questions, right? So are there any questions about what we've discussed today? I'm going to stop recording. I don't think I have anything. Yeah, I'm going to go ahead and stop recording.